Temperature and heat are different but related concepts. Temperature is an intensive quantity and heat is extensive. And what that means is if we have a certain amount of, say, 10 kilograms of iron heated to 50 degrees Celsius and take half of that iron away, we've reduced the amount of heat present because we've reduced the extent of the iron. We haven't changed the temperature. We can also see the temperature of a cup of coffee is higher than the temperature of the ocean, but the amount of heat contained in the ocean is ridiculously greater than the heat contained in a cup of coffee. The definition of temperature we're going to use is the average translational kinetic energy of the atoms or molecules that make up an object. And heat is really just a form of energy. We observe experimentally that if we have two objects in thermal contact, we'll see heat flow from the higher temperature object to the lower temperature object until they reach a common temperature. As far as what scale we should use, you should have already used the Celsius scale where you have water freezing at 0 and boiling at 100, but there's a problem with this. If we're looking at the weather and someone mentions that it was, say, 35 Fahrenheit last night and it'll be 70 Fahrenheit today, you might hear them say it'll be twice as hot, but of course it won't really be twice as hot. We can imagine if it went to 1 at night and 70 during the day, is that going to be 70 times as hot? And of course if it went to 0 Fahrenheit at night, 70 degrees the next day would be infinitely hotter, much less what would happen for negative temperatures. So we need an absolute temperature scale. We could have an absolute Fahrenheit scale or an absolute Celsius scale, meaning we use degrees that are the same size as Celsius or Fahrenheit degrees. If we did that with Fahrenheit, we'd have what's called the Rankine scale for absolute temperatures. And what we would do is just add 459 degrees to any Fahrenheit temperature, and we'd have its temperature on the Rankine scale. We're not going to do that, though. We're going to use the Celsius scale, where absolute zero is negative 273.15 degrees Celsius. So we'll add the complement of that, positive 273.15, to any Celsius temperature to make it a Kelvin temperature. Additionally, we don't use the degree symbol on the Kelvin scale, so 20 degrees Celsius is 293.15 Kelvin rather than 293.15 degrees Kelvin. The first thing we can do looking at this is look at thermal expansion. This you've probably used before. If you've got a metal lid on a glass jar and you can't get it unstuck, you might run hot water on the lid. The reason this works is the metal in the lid will expand more than the glass in the jar, and it'll be easier to open up. We can make a model of this expansion as a linear process because that's the easiest one, that's the simplest guess. And we can say that the new length of a heated rod should depend on the original length, the temperature change, the makeup of the material, and figure out the new length that way. We do expect this to be material dependent because we don't think everything will expand the same way, otherwise the glass jar and the metal lid trick wouldn't work. The expression we get is that our new length L is equal to the original length times this material dependent constant times the temperature change. The temperature change, notice, is the same whether we use Celsius or Kelvin because there's still 20 degrees between 0 Celsius and 20 Celsius, or 273 Kelvin and 293 Kelvin. We can find the change in length as L0 minus L by writing L0 alpha delta T is equal to delta L, and we can write that as L0 times 1 plus alpha delta T. This is in general going to be a very small change, but the effects can be very large. If we have a couple of pieces of sidewalk and each one is 3 meters long in the winter, and we have them fitted very tightly together, sometime during the summer we might see their temperature go up to 40 C. The new length associated with each of these will be 3 plus 3 times the expansion coefficient for concrete times 40 degrees Celsius. Now this expansion coefficient is a very small number. It's essentially 12 parts per million per degree Celsius. So the new length of the concrete is only about 1 millimeter longer, 1.5 millimeters longer than the old length. And it seems like that wouldn't make any difference. However, the concrete will buckle and pop up, and we can figure out how high this pop-up will be by saying the 3.00144 is the hypotenuse and the 3 is one of the sides, the remaining side of that triangle is the height of the buckling in the road. Here, notice we get a ridiculous 9.3 centimeters. This is almost 4 inches. This is the reason why sidewalks aren't made like this, and people use expansion joints in construction where they leave room for it to expand. Sometimes you'll see interlocking metal teeth on a bridge that can slide back and forth so the length is free to change a little bit. You can do something useful with this thermal expansion if you put two different strips of metal together, for example brass and steel. If we imagine tack welding these together, they have two different coefficients of expansion, and for a given increase in temperature, the brass expands more than the steel. So what we would see is the metal strip will curve one way or the other, because if the brass is longer than the steel, we'll see this, assuming we have the left side of this tacked down, we'll see this lift up and possibly touch a contact here. When it cools down, it will relax back to the horizontal and possibly touch a contact here. This is the simplest kind of thermostat we can imagine. So up here, if it reaches this upper contact, it turns on the air conditioning, and if it reaches this lower contact, it turns on the heat. This is called a bimetallic strip thermostat. In addition to linear expansion, there is, of course, volume expansion, which is sometimes interesting. This will happen both in liquids and solids. We don't worry about this with gases because for gases we have the ideal gas law, which tells us PV equals nRT, and that's how we'd find the change in volume there. But for liquids or solids, we can model what we did, follow the same process that we did for length, and say the change in volume is initial volume times some material-dependent constant times delta T. Now, we don't actually have to have a whole new table of beta values, this volume coefficient of expansion. If we imagine we have a cube and we watch it expand in all three dimensions, we would say its original volume, V0, is L0 cubed. We can plug in our formula for linear expansion, and we get L0 cubed times this factor 1 plus alpha delta T cubed. We can then expand this, and we get all these terms. However, keep in mind that alpha delta T will always be small. We don't see things expand by 40% or something like that. Even for a large temperature change, we won't see much expansion because we can do some math, and by the time the expansion gets significant, we've typically already melted or vaporized the material. So we don't need the term that's cubic in alpha delta T. We don't need the squared term. The simplest one is just the linear term. So this is an approximation, but we'll see it's very good. Ice changes size significantly when it's heated or cooled, and alpha is still only 51 parts per million. If we make this approximation that the change is proportional to 1 plus 3 alpha delta T, what we get out of this is that our volume coefficient of expansion beta is just equal to 3 times alpha.